Hello, welcome to the second part of photoelectric effect. Today we begin with Einstein's photoelectric equation. Very fast, when an electromagnetic radiation is shown on the surface of a metal, electrons may be ejected. So we say maybe because depending on the energy of the photon, it may or may not be ejected. So it has to meet the threshold, which is the work function. Now, a photon of energy, HF, where H here is Planck's constant, and F is the frequency, penetrates the material and it will be absorbed by an electron. Now, if enough energy is available, then the electron will be raised to the surface. And if it is even more than just raising it to the surface, it will be ejected with some kinetic energy given by that expression half mv squared, where m is the mass of the electron or of an electron, and then v is the velocity at which it moves. So energy of that photon can therefore be given in terms of the energy needed to remove an electron from the metal surface, which is the work function, plus that excess energy above the work function, which is now giving it the maximum kinetic energy that it gains, that particular electron. Yeah. So we can express that as HF is equal to W naught, where W naught is the work function, plus the kinetic energy of the electron. Now, that's just the same thing as work function in this other equation. We are now writing it in terms of Planck's constant and threshold frequency. Now, these the letters that are used, like H is Planck's constant, M is the mass of an electron, F is the frequency of the incident radiation, V max, V then, this is subscript max, is for maximum velocity of the emitted electrons. Then F naught is the threshold frequency, W naught is the work function. So let's look at the factors affecting photoelectric effects. So one of them is the intensity of the incident radiation. So some say it's the brightness. Intensity could just be like the amount or the radiations that are hitting a particular surface per unit time. So the number of radiations that are incident on a unit area per unit time. So you can simply also just look at it in terms of the brightness of the radiation. Then applied potential difference between the plates. Thirdly, we have frequency of the incident radiation, and then we can also talk of the type of metal. So at this point, I want us to look at a simulation just to try to help us understand how these factors affect photoelectric effect. So this is from PhET, a very, very good resource for simulations. So there are certain things that we may not be able to, or rather certain experiments that we may not be able to conduct in our labs because maybe you don't have certain apparatus. So that is when it is very, very important for you to have simulations because it can help the learner understand easily that concept, more so when it comes to three-dimensional things, which may not easily be expressed by just drawing on the board. Now, so let's begin with the intensity. So as you can see, there is the intensity here. So we have wavelength can be adjusted there. Then we have the two plates. So we have that metal plate. Of course, we have the metal plate here where the radiations fall on. Then we have the source of power. um, yeah, the voltage supply here. So you can vary it and then we see what happens to current. What else? Yeah, we have graphs. So as we do all that, we can also observe the change in, say, light intensity and current, or current versus the intensity. Okay, so let's begin with the, so we'll be using sodium. So if you look at, we have sodium, we have zinc, copper, platinum, and calcium. Now, so let's look at how current varies with intensity. So here is the switch. So we can connect it, and then we see what happens. Yeah, so that is, I think it's on, but then nothing happens. Oh, there's no radiation at all falling on the metal surface, so at least, yeah, so you can see then electrons are ejected, they're moving to the other side, potentially just 0.8 uh, 0 volts. Then that is our graph. So what happens as we vary the intensity? So look at that. Yeah, look at what happens to the current as the intensity is increasing. At this point, it's at 72%. So as we keep on moving, you can see that there is linear kind of relationship whereby current varies directly as the intensity. Okay, that is in as far as intensity of the incident radiation is concerned. Let's now move to energy of the incident radiation. So I think there we can talk about not really energy versus the light frequency. Yeah, so the incident radiation has certain frequency and we can vary it. So in this simulation, we'll be able to vary that frequency and see what happens. So if you look at what we have in this simulation, there's infrared and then there is ultraviolet. So as you move along, so you're moving from ultraviolet all the way to infrared. So in between, if you remember what we have in the electromagnetic spectrum, so from ultraviolet, you go to violet, all those other colors in between, and then you move to indigo. Not really. Yeah, I think you know how to get the members of electromagnetic spectrum. Here, we are strictly concerned with light, and light has those 7 members: violet, indigo, blue, green, yellow. Yeah, name them. Okay, so as you can see, from ultraviolet to infrared, the wavelength is increasing. And there's something with the electromagnetic waves. As the wavelength increases, the frequency decreases. So if we were to vary frequency, then we can have it from this extreme end where we have the maximum wavelength, that's the minimum frequency. So we can begin from here and see what happens. So as we do that, so minimum frequency to maximum frequency, from infrared to ultraviolet. What happens? I want you to observe this graph here. So what happens? Intensity is constant. All other things are constant. You just vary the frequency. So as we reduce the wavelength, we are increasing. We are increasing the frequency. Look at even the electrons, the number of electrons ejected. Okay. Something, you observe also the current down here. So what happens to the current? Yeah, the current is increasing. And that's the reason why the graph of energy in electron volts versus the frequency is a linear one. Yeah, that kind of relationship is also linear, just like the one we looked at previously. So we can say that the energy of these photoelectrons is directly proportional to the frequency of the incident radiation. Very good. So we can put this somewhere here. Intensity, no problem, because we just want to have it somewhere constant as we move to the next investigation. So we can look at current, now current against the voltage. So the voltage across the terminals here. So we have been using 0.80 volts. So I want you to pay keen attention to our graph. So what happens to it and what happens to the current down here? Yeah, look from 0.8 as we move to the right. Yeah, nothing. Why? Okay, let's move backwards. Oh yeah, it's changing. I wasn't very keen. So it's changing. So that's the maximum current we can have, but look at that graph. Then as we move to the left, it's constant over some time, and then, wow. So when the voltage is 0, look at the current, it's maximum there. Then all of a sudden, when we're supplying negative current, negative voltage for that matter, look at, negative voltage. I think that is as when we reverse the terminal, that's what it means here. So when we reverse the terminals, because as you can see, it shifts. Now we have positive. When we take it to this end, it's positive on the right hand side. When you take it to this end, it's positive on the left hand side. So look at what happens. Actually, if we were to use light of a higher frequency, then let's see what happens to that graph. It's raised a bit. Yeah, it's raised. Now it's raised. Okay, we've changed the frequency to a higher value, but then it's maintained at a constant value as we vary the potential. Yes, so look at that. So the shape still remains the same. Now, those are the three that we can investigate here. But rather, we also talked about the type of metal. So we'll look at this kind of variation before we move to the type of metal. At first, as you increase the voltage, say from this value -2 to 0, from whatever we have displayed on the graph, there is increase of current until it reaches a constant value. So after that point, now it's constant throughout. Now, if at all we were using, that was for sodium. Now for sodium, and then look at it. Just we want to have, say, the intensity of the incident radiation is constant. But then what are we varying? Look at this. Nothing changes. Current, oh no, this is current versus battery voltage. So we don't expect any changes. We vary the frequency of the wavelength. So we don't expect. Rather, it will change if we varied the voltage down there. So let's investigate different metals. So the first one was sodium. Look at sodium and the frequency. So we go to frequency, electron energy against frequency. That's for sodium. Let's see what happens. Look at that. I wanted to cut this axis, but anyway, you get the idea. Yes. So look at where it cuts the axis. That is sodium. So just want you to bear in mind, it's approximately somewhere below 0.75, and everything here is to the power of 15 hertz, 10 raised to 15 hertz. So look at that is for sodium. So if we move to another metal, zinc, we do the same. So we're varying the frequency. Look at what we are getting. As you can see, now it is between 0.75 and 1.50. So it's somewhere in the middle. And that is also times 10 raised to 15 hertz. Yeah, so this value is higher. This value is now greater than that of sodium. I think that is pointing something towards the threshold frequency. So this one requires a higher frequency just for the electrons to be removed or dislodged from its surface than sodium. So let's look at copper, for instance. So when we deal with copper, yeah, look at the kind of curve as we vary the frequency, look at the kind of curve. Somehow closer to that of our previous metal, that is zinc. Yes, closer to that. Its threshold frequency is almost close to that of zinc, but slightly higher. I think it's slightly higher based on what I'm observing here. Because other factors have been held constant. Intensity is constant at 72%. And then the voltage is also constant. So we are using negative value here. That is serious. Okay, maybe we can have it somewhere there. Then we investigate sodium once again. Yeah, look at that. Yeah, somehow still at the same point where it was. Then we go to zinc. Let's have a look at that. Yeah, it's just where it was. Then we move to copper. We vary the frequency as we reduce it. Look at what happens. They are still at the point where it was previously. Yeah, slightly higher than that of zinc. Then we move to platinum. For platinum, yes, it's higher than all of them. So that's at 1.5 times 10 raised to 15 hertz. Well, I think that's enough for us to make our summaries about the factors affecting photoelectric effect. Okay, back to our factors. We can now summarize and say, as for intensity, the rate of emission of photoelectrons is directly proportional to the intensity of incident radiations. For applied potential difference between the plates, what did we see and what can we deduce? So we can summarily say that the rate of emission increases with increase in the potential difference between the plates until it reaches a maximum value, which is now the saturation point. So once it's saturated, then it remains constant. I think in our simulation, that was very clear. Frequency of incident radiation. So I think this is what will affect the work function, and we can say that each metal has its characteristic work function, hence a characteristic minimum frequency for photoemission. So that has to be overcome for photoelectrons to be emitted from the surface of a metal. Then lastly, we have the type of metal. So for the type of metal, each metal has its value of work function, which the incident radiation must overcome in order to have photoelectric emission. I think that's the last simulation that we saw from PhET. Now, I want us to move to something known as stopping potential. Diagram, just like what we had there. Yeah, so this is a potential divider. Then those are the radiations. So we have light, electrons ejected. They move to the positive terminal here, the anode. Then we have connected a voltmeter across the terminals of the apparatus. So highly evacuated. There's, yeah, look at that for evacuated. It should be evacuated, quotes tube. Evacuated, meaning that you kind of drain air out of it. So there shouldn't be air inside the tube. The reason for that is so that you minimize the collisions between the air molecules and the electrons, because that will in turn affect the energy of those electrons. So it might deprive them of the energy that they need to reach this other plate. Now, Yes, so there is also an ammeter here, just measuring the current. So in most cases, a milliammeter is used because the current may be little. So for you to have a proper deflection, you need a milliammeter in that case, rather than an ammeter. Okay. Um, so in this figure, the voltage is varied by moving the jockey R. The jockey is a movable contact from X to Y. Then the voltage uh, which just stops the electrons from reaching the negative plate is found. I think it's just something that as I was varying in that simulation, if you're keen, you could have seen that as we were varying the voltage, as we're moving to the left, yeah, there's a point where the electrons were stopping from, yeah, were being stopped completely from moving to the right-hand side. So at that point, again, if you can go back to, you can just go back to what we did up there, you will notice that the current is zero. So the current that is registered on the ammeter or on the milliammeter is zero. But then the voltage is a kind of some negative voltage. So that's what we call the stopping potential. So at that potential, where no electron has sufficient energy to reach this other side here, and the current registered is zero, is what's called the stopping potential. So the voltage which just stops the electrons from reaching the negative plate is found like that, and the voltage is known as the stopping potential. I think you now know what stopping potential is. Now, you can obtain various values, like in this question here. So in an experiment to observe photoelectric emission from a clean its cesium surface, the following readings were obtained. So let's have a look at the readings that were tabulated. So stopping potential all the way, frequency times 10 raised to 14 hertz. Now, plot a graph of stopping potential Vs on the y-axis against the frequency on the other axis. After that, from that very graph, you are asked to determine the threshold frequency, and the answers are given here, the threshold wavelength of the surface, and then the Planck's constant, finally the work function. Okay, I did that in Excel. So this is the graph that I obtained. Stopping potential against the frequency. If you study it, it's a straight line graph, actually line of best fit. It's a best fit line. And it was fortunately passing through all the points that were given up here. Yes, so fortunately for us, there were no outliers. Now, look at the point where it cuts the frequency axis somewhere there. And then there is also this point where it cuts the other axis, the stopping potential axis, the y-axis. So that is the graph. It's drawn. I drew mine from Excel. You can draw yours as well on graph paper. Now, how do we get the threshold frequency? From Einstein's, and this is why Einstein's photoelectric equation is important. So from Einstein's photoelectric equation, yes, we've already discussed that. We have this, so this kinetic energy can be expressed in electron volts. So you rearrange, and then you have EVS is HF minus HF naught. That's now mathematics. So that's why mathematics is very important in physics. So for a physicist, it's just important that you are good in mathematics. Now, you make VS subject of the formula, and then this is what you end up with. For sure, because we are plotting potential, stopping potential VS against F, the two are the variables. VS and F are the variables. All other things are constants. Now, from the equation of a straight line, HE is therefore the gradient. H over E is the gradient, then negative H, F naught over E, all that is C, the y-intercept, the point where the graph cuts the y-axis or the stopping potential axis. So we can compare the two equations up here, these two equations, and then, yeah, so when we compare these two equations, yeah, the two equations up there, yeah, we can say that when the stopping potential is zero, at the point where stopping potential is zero, yeah, we have that, so that, what is it? F naught, because H over E, H over E. So what will remain with is F is equal to F naught, and that is the x-intercept. So threshold frequency is gotten by simply checking the y-intercept, the x-intercept, I mean, so the point where the graph cuts the x-axis. Well, I may not be able to get this exactly, but I used the equation. I generated the equation from Excel, and the x-intercept from that equation was giving me 4.5 times 10 raised to 14 hertz. Threshold wavelength, now just use this formula, which we had also looked at earlier. I think that one you can do, just substitute the values where C is the speed or velocity of light, and then you already have the threshold frequency, then that gives you this Planck's constant. So looking at this question, looking at this equation once again, it's clear that the gradient will just be H over E, as I explained earlier. So H over E, you get the gradient from your graph. Please obtain the gradient from the graph. And then mine, once again, because I just did it from Excel, and Excel generated the equation for me. So from that equation, the gradient was 0.4. So 0.4, obtain yours, and then you multiply by Planck's constant, which is given. So use the value. Not really Planck's constant, but this is E, yes, charge on an electron. So charge of an electron, which is 1.6 times 10 raised to negative 19. Then you get 6.4 times 10 raised to negative 30, depending on the gradient that you obtain from your graph. So there might be slight variation, but it should just be around somewhere here. So work function, now that you have H, you use your H. So the value I obtained was 6.4 times 10 raised to negative 34 joules second times the threshold frequency, and then that's what we get. I think having looked at that, we can move to application of photoelectric effect. So where do we apply it? So photoelectric effect is applied mainly in photocells. So a photocell is a device which converts electromagnetic radiation and the electromagnetic radiation directly to electrical energy. Now, we have three main types of photocells, which are photoemissive cells, we have photovoltaic cells, and then photoconductive cells. These are also known as light-dependent resistors, which really find application in many areas these days. The rest, you can as well do your research, find how even these light-dependent resistors are applied in the household, appliances, in vehicles, in trains, in buildings, and what have you. Otherwise, that marks the end of our lesson. Thank you for listening.